Well, thanks very much to Delma for introducing us all, and welcome along to Weather for Sailors for this evening. So we'll start off with the next slide. Thanks, Robin. Give me the next slide. There we are. So just for everybody, the most important thing that you do here is if you look either at the bottom or the top of your screen, you will have a view button. And if you go to that view button and make sure that you choose to focus on content. So if you go to the view button and focus on content, Delma's shown you where the chat button is. We won't be using Q&A. Please, we'll make sure to keep the bandwidth off. Everybody's camera will be off so that we can increase the bandwidth. And you've all seen how you can raise your hand and how you can chat. And I'm about to launch the first slide, the first poll, so you'll get a go at that. Righto, Robin, next slide, please. So just to give you a thing about who's talking to you not. My name is Simon Dryden. I've been in the ORCV forever, and Robin has been there forever and a bit more. And so Robin is very knowledgeable on weather, and so he will give you a good example of how weather influences your sailing and what to do about it. Next slide, please, Robin. All right, so I'm just going to launch a poll. So if you could all go in that poll and answer the question, what sort of sailor you are, whether you're racing, cruising, powerboat, or you're involved in search and rescue. That's a special one because we've got a few from the Coast Guard this day. So if you all go and put your answers in there, on your screen, you will see that poll come up. And you can put your answers in. Okay, so we've got 50% cruising, 35% racing, 15% search and rescue. So have we got anybody else? Okay, 39% racing, 48 cruising, and 13 for your search and rescue, Robin. So there, we're done. Next slide, please, Robin. And now we're just going to launch a poll. What's the most important thing if you're rescuing people or you're sailing or cruising in the bay? So here's the next poll. So if you could just pick your answers there out of all those things, see what you think that might be. Well, Robin, you got 100% people who just are concerned about the wind. All right, now we're going to hand over to Robin. So if you could all give yourself, and you can see there's some responses there, you can give him a clap and welcome Robin to the 2023 Fundamentals of Weather. Welcome, Robin.
Thanks, Simon, and good evening, everybody. You should have by now had a look at all the definitions. To explain them all takes an awful lot of time. We have a lot of stuff to get through, and I'll just look at two of these. And I'll just repeat, weather is what we've actually got, whereas climate is what we expect based on historical information. The next most important thing, and a difficult one to get hold of, is the pressure, temperature, and volume relationship. These are a constant. When you alter one or two of the others will change also. And let me explain that. If you've ridden a push bike and you had to pump up the tyre, by using the pump, you press the handle in and the volume of air in the pump is decreased. And as it's decreased, the pressure goes up and it gets to the stage where it'll go through the valve into the tyre, and at the same time the pressure's increased in the tyre. After a little while, if you're holding the end of the bike pump, you'll feel that it's hot. And this is one of the simple rules. Increase the pressure and the temperature will rise. Decrease the pressure and the temperature will reduce. So we do this in this example by making the volume smaller so that the pressure goes up and the temperature goes up. And the other one that gives people a bit of trouble is relative humidity. And that is the atmosphere has anything up to 5% of its volume as moisture. And that's termed saturation. Most usually, the air around us is about 2% of moisture. And if it'll hold 5%, then, and it's only got 2%, then the humidity is 2% of 5. If you take, for example, cooking, and you want to dissolve sugar in water, you heat the water and then the sugar dissolves quickly. And it's like that with the water vapor. If you increase the temperature, it can hold more water vapor. And if you then decrease the temperature and the water vapor is not capable, the air is not capable of holding that amount of water vapor, the water vapor will condense into fog or cloud, and eventually those droplets will form and fall as rain. So if you take air at ground level and rise it, the pressure decreases as it rises, and it will become cold, turn to water, and eventually ice. So, moving on now, the air at ground level is at a common pressure of 1,013 hectopascals or millibars. They are the same units. A barometer, a standard barometer at 1,013, if you divide that by 1,000, you get a millibar. And hectopascal is a pressure term that is scientifically used. In America, they use inches of mercury, and it just depends on what the standard is in that particular locality. Anyway, a hard concept is that air has weight. At ground level, air weighs somewhere near 1 kilogram for a cubic meter of air. If you think of that cubic meter of air as a building block and you stack another cubic meter on top of it, the weight goes up. And if you continue to stack air on top of it, you get more and more pressure, more weight at ground level, and you get a higher pressure. If you were to take that stack of blocks all the way up to the top of the atmosphere, at about halfway up, for example, and you measured the pressure there, you've only got half as many blocks. You only get about half the pressure. And that pressure generally is at about 18,000 feet. That's half the atmosphere. And that has a pressure of 500 hectopascals halfway up. You get up to around 59, 60,000 feet high before that pressure becomes zero. That's the top block of air, if you like. So in this diagram here, you can see as you go up that the pressure is higher. If you measure the pressure, it's usually measured by a barometer, and the standard barometer that most people use is termed an aneroid barometer. That's the round one with the needle in it. And it's worth remembering, if the reading from a place that's up in the air, higher up, in this case a dwelling up on the hill, then the pressure will be less because he's already several building blocks of air higher. And you can use a barometer as a result to determine your height by comparing the pressure with what the height would be. And this is the basis of a altitude meter in an aircraft. It's basically just an aneroid barometer, or a barometer. There's a lot of electronic ones nowadays. But you can use the reading to determine your height. The other thing is the atmosphere with a system that's moving across the ground as high pressure or low pressure. It can be read by the barometer, and the characteristics that result are used in determining weather to a large extent. In the 98 Sydney Hobart, when so many boats were in trouble and lives were lost, only a third of the yachts had a barometer on board. If they'd had a barometer on board, things would have been very different. Here's a diagram of 3 different types of barometer. On the left is the inches of mercury, which was the very first kind of barometer invented. The aneroid barometer is the one in the center. They are fairly cheap and quite common. On the right is an electronic barometer, which probably are more common nowadays. In order to get a good reading that corresponds to the Weather Bureau, your barometer might need adjusting if it's been knocked, or if it's new, or if you've changed your locality, or in the case of an aircraft using it as an altimeter, the airports broadcast the correct pressure at the aerodrome, and the pilot adjusts his barometer to suit. There is an adjusting screw in the back of the barometer, and you can turn the screw a little bit one way or another to adjust it. Now, there are videos on the subject, and through the course, you may wish to see a video on a particular aspect. When you go to the ORCV website and you look at the subjects, the arrow here, that's this arrow here, points to the weather segment. And if you click on that, you go to useful videos, and you can click on these to download a clearer explanation, perhaps. Now, this overview is something you should have read. It explains what we're trying to do is to equip you with the tools and information so that you may make better decisions. And one of the things we'll come across quite a lot in weather are vectors. If you're an engineer or some kind of science person, you'll be very familiar with vectors. Vectors are a graphical representation of directions and unit measurement of some value, such as knots of wind or distance or something like that. And a scalar vector only requires a number to define their magnitude. That is distance, speed, temperature, relative humidity, cloud cover. Whereas a proper vector can use direction as well as a number. And those examples are velocity, acceleration, force, friction. In sailing, common vectors are wind, tide. Tide has a number and a direction, or currents. And this is an example of what a vector looks like and how somebody might mathematically use it. You have boat velocity in this example of 4 knots. If you were to measure the length of the vector, it would be 4 units. And whereas in another example, the actual velocity of the boat making 1 knot is 1 unit, and the tide in this example is 3 units. So you may join the vectors together or take one off the other, and that's how you would depict the answer to something you're trying to represent. This is an example of adding vectors in direction and units. A sea breeze always blows at right angles to the shore. If you have an existing wind such as the gradient wind, the question might be, what's the wind going to be for me sailing? And by using vectors in a triangle, you can get the answer. In the diagram on shore, it shows you the resultant wind, which is what you will feel in your vessel. And on the diagram on the left, you have a boat sailing in tide. And the tide is, in this example, moving at right angles to the direction you're heading in. So your boat's moving at 4 knots. It is 4 units of length on the vector, and the tide at right angles of 3 knots is shown as 3 units of the same length. And the answer when you join them is that your boat is actually moving in this direction at 5 knots, and the length of this vector is 5 units. And there are many examples where you can solve problems if you wanted to. I'm telling you all this because the weather diagrams use vectors a lot, and visually you can look at them and see the differences. And particularly one is convergence, all the way through weather aspects. Convergence and divergence are very common terms. Convergence is where 2 forces come together, and divergence is when a force splits or somehow alters. Let's say you have an original wind here and you're sailing along the shore, and you come to a valley or the side of a hill, and another wind is coming out around that and blowing the join on to the original wind. The question is, what is the new wind? If you're trying to work out it's going to be stronger, for example, do I need to change sail? Or is it going to drop out? By joining the 2 wind strengths together, you can get an idea of what the new wind is. You can calculate it if you want, but mostly the question as a sailor is, what's going to happen when I sail past this valley? This is a tidal diagram of the tide chart in Bass Strait. And here we have a current flowing through Bass Strait. And as it reaches the sharp corners, and sharp corners is a term we'll use quite often as to what happens to wind. But when you look at the vectors, in this case, the direction of the tide is shown by the arrow, and the strength of the tide is shown by the length. So the vector lengths are relative. Stronger tides have longer vectors. And this is another example, but the vectors in this case are shown by the density of small arrows. if you use it or windy.com, they show the wind in direction by the small arrows, the flying arrows, and the strength of the wind is given by the density, the number of arrows, and also by colour. If you're not familiar with windy.com, when you look at these clear patches, they represent no wind. So there are no flying particles in that area of no wind. Now some basic laws of motion. You can read that. I want to give you an example. If you've had a car breakdown or you've assisted in a car breakdown and you have to get it off the road and you get out and start to push, the car doesn't move until you reach enough power or force to start it rolling. So it won't move unless you start to push. If you need some help, some more people come and help you to push the car off. And the net force is the combined pushing by each of the people assisting you. If they keep pushing, the car goes faster and faster. It increases its velocity. If the car stops again, that's all forces are equal and opposite. That means it's stationary and the resistance to it rolling, in the case of constant velocity, the resistance to it moving is equal to the amount of force that's trying to make it move. If you get it moving, it will keep moving until the force of the resistance or someone else pushing it from the other end or putting the brakes on stops it moving. And there's a video about that if you need it. This is an example of why a yacht can sail to windward, and it shows you some of the vector diagrams that can be useful in working out or explaining it. I'm not going to do that. I'm only trying to show you what vectors can be used for. Now here's an example, and you can read it. Let's say you're trying to have some guests and you want to take them for an afternoon sail. You're going to go up the Yarra and the tide's running out after some rain. And what time must you begin to get everybody back on time? In the wind direction, when you round a mark, it's a similar problem. What sail am I going to need? And what direction will the wind be? Is it a spinnaker? Is it hard on the wind or what? And here's the example. It's the same as the sea breeze. You sailing up to the mark, let's say along here, the wind is blowing in this direction, and when you round the mark here, what is the strength and what is the direction going to be? Now you may have instruments on your yacht that'll solve that for you automatically, but if you have to calculate it, it's something like this, or more likely, if you're rounding the mark, you know because you've sailed the boat a lot. There's someone saying they can't see the pointer. Yes? Hmm. Is that coming through? The- A lot of people saying no. Okay. Okay, so that this diagram shows the due direction and how strong the wind is if you measure it. Even if you're not mathematically inclined or that's a bit hard, then you can visualize it, and that's sufficient. And here's another one. You can make 5 knots upstream, and there is a tide running of 3.5 knots. And when you get to the other end, you're going to get some coffee at the boathouse. And then when you come back, you're going to have the tide with you. And you're working out so that you get your guests back in time. Now, mostly you don't sit and calculate. You do this mentally. But that's how you use vectors. I want to turn around now and look at the seasons and what they mean. And Earth actually spins 24 hours for one spin. And the thing is that it doesn't spin in the on the axis is a constant slope of 23.5 degrees. And because of that, as the Earth goes around the sun, it faces the sun in different directions, summer and winter. Explain that a little bit further. But the orbit around the sun is also not perfectly circular, and sometimes the sun is closer to the Earth and sometimes it's a bit further away. If we look at this example, here is the axis of the Earth where it's spinning, and the sun is over here and it's shining onto the Earth, and in this case the south summer solstice. You see the sun is delivering the same energy in each one of these columns, but the angle that the column has when it's on the Earth is different at the South Pole and the North Pole. Because of the inclination of the Earth's axis, the South Pole in this case is leaning more towards the sun, whereas in the North Pole, the Earth is hitting the surface and leaving the North Pole in shadow. So there is nil radiation covering the Earth at the North Pole. And so as the Earth spins, they don't get any sun at all, and that is the 24-hour darkness of a winter. Whereas at the South Pole, as it spins, it's always facing the sun in the summer, and they have 24 hours daylight. And going around the Earth at the equator, it's near enough that they get maximum radiation all the time. Whereas if we look at the equinox, and that's when the Earth is spinning in its orbit halfway sideways from the sun. Can you see the pointer, Simon? Okay. So that the amount of radiation on the Earth is the same North and South Pole, and the spring and autumn solstice is 23rd of March and 23rd of September, and that's when the daylight is even on the Earth, and the equator is still receiving the maximum amount of radiation. And coming back to the winter solstice, 22nd of June, we have reverse of the summer solstice. The North Pole is now inclined towards the sun, and as the Earth rotates, they get 24 hours of daylight. And in the South Pole, the South Pole is in the shadow of the Earth here. So correspondingly, it's called less radiation towards the surface as we go around. You'll see that the other aspect is that the beam of radiation on the curvature of the Earth has to spread over quite an area compared to at the equator where it's full on. So the equatorial region has similar radiation all year round. As we get on the world, as we grow up, we're looking at the world, everything's flat. And it's not only flat, but we get maps. Everything is depicted as a map. We see plans and everything's flat. But the truth is, the Earth is not flat, it's a curve, and maps and so on are adjusted so that we can visualize in a flat plane. But the Earth is rotating, and if you're familiar with horizon, even if you look out to sea, you can see a boat sailing away, it gets lower and lower on the horizon because of the curvature of the Earth. Now, according to what we said, if you have in this diagram above, if you have a curvature and something doesn't go straight, there must be a force pushing the thing. It's called the Coriolis force, and it affects the motion of the wind and currents. And a lot of the characteristics will show you, probably more so in station 3. Anyway, Coriolis force is a construction so that we can use Newtonian physics to explain things. And we'll have a look at that. This is what we do with our intellectuals. We give them examples so that they can understand. Here we have two boffins sitting on a merry-go-round, and they're throwing the ball to each other. When it rotates, they miss and they can't catch it. And this is trying to explain what's actually happening. When one throws the ball to the other has rotated and is no longer where the ball was thrown to. You see the ball is thrown in a straight line in that example, but the seesaw has moved around. So Newtonian physics says in order for the ball to move like that, there must be a force making it change direction. But if you look from above them, that is, in space, the ball is still moving in a straight line. It is possible to estimate what the change in position might be, and you can adjust for that. So let's have a look at why this occurs. As the Earth rotates, and this is taking slices through the Earth and saying at the circumference, this is the speed at various latitudes that the surface is actually moving. At the equator, of course, it's constant. And these two directions here is saying if you've got wind moving this way, it will appear to actually blow in this direction if the wind's going from the equator to one of the poles. So the Coriolis effect has a different speed relative to the latitude, and that is, if you're on the equator, you are moving through space at 1670 kilometers per hour, whereas at the pole you are just turning around, and at some other latitude you're moving in these other speeds. Now here's an example which explains to me the whole thing much clearer. Let's say we're in an aeroplane in Melbourne and we're going to take a flight to Sydney, and it takes 1 hour. The plane sets off from Melbourne to Sydney, but the Earth at Melbourne is travelling, the surface is travelling at 782 knots, whereas Sydney is actually travelling through space at 872 knots. In the hour it takes for the plane while it's in the air, Sydney has moved in space relatively by 37 kilometres. So in order to get to Sydney, the plane has to travel in this, he has to estimate and set his compass course to go this way, so that by the time his hour is up, Sydney has moved from there to be where he's going to be. And more importantly, if the plane takes 2 hours to get to Sydney, it's going to be, Sydney will have moved 37 knots or miles plus another 37 miles. Or if you speed the plane up so that he only takes half an hour, then Sydney will have only moved a half of 37 miles. And the pilot must set a course, in that case, to go here. So let's have a little break and see if you can digest that. In minutes. Yeah, okay, I'll try and get that I can show where the pointer is. If you look at your notes, if you downloaded the notes that are there are diagrams with a lot of this, and I encourage you to keep the notes in the future, because we're recreational sailors. We don't go out day after day after day, and we don't experience many of these things constantly. So after you've been sailing and you wonder about something, if you come back and look through those notes, the penny might drop a lot better. And even in 3 years' time, if you refresh your learning with those notes, the penny will drop even better. And that's the way it goes. Things that didn't seem logical at the time make sense a bit later or become clearer.
Simon. Okay, I can see the pointer now, guys, on the screen. So Simon and Robin, can you just have a little practice with that pointer and I'll tell you that we can see it? Just that's one of the comments coming through, please. So we can see the pointer again now and we can see it moving across up to the horizon. You've just gone up near the sun. Okay, you're right on the sun now, so that's looking good.
On the sun?
Yep,
on the
we're
boat?
on the sun. So that's good now, Robin. Robin, if you're talking about the pointer and we can't see it again, we'll just stop you next time.
Yeah.
Okay. You go and have a little break for a minute.
Okay, a couple of minutes before we start again, so gather round. We'll get underway in a couple of minutes. All right, we'll get back underway. This time, for those of you who had trouble seeing the pointer and the marks, we'll make sure that this time Robin will describe what he's doing till we can sort that out. So welcome back, Robin.
Thanks, Simon. We're going to have a look at this section at the global weather patterns arising from Earth's orbit. And the Australian weather map as a tool and reading it. We want you to be able to read a weather map because in the world, the weather map is universal. Even if you can't understand the language or the numbers, the diagrams are the same worldwide. We'll look at high and low pressure systems and the barometer response to them, and how to understand a weather map. So let's look at that a bit more. The atmosphere is depicted in this diagram. At the equator, it is a much thicker belt of air. And the reality is, we take our block of air at the equator and we get maximum heat radiation from the sun. And that block of air expands and it becomes lighter, and so it rises up into the atmosphere, the hot air balloon effect. And as it rises, if you remember, there's less pressure, less air on top of our block. So as the pressure decreases on the volume temperature pressure relationship, as the pressure decreases, the temperature decreases also as the volume expands due to less pressure. And if you continue that going up, it passes, saturates the moisture in the air, passes saturation, and it gets colder and colder. It turns to water, which is why you get so much rain at the equator. It turns to water, and as it goes up further, it turns to ice. So we get hail, snow, all that sort of thing. And it goes all the way up to around 59,000 feet high, higher than what the jets actually fly. And it's extremely cold, so that air has become cold, and as the wind sinks, because as it's got cold, it's become more dense, more heavy in the other air around it, and it sinks, as he said in the video, at about 30 degrees latitude. Now 30 degrees latitude is roughly our area where we are, Sydney, Melbourne, and so on. It's our sailing territory, particularly. So the cold air sinks, but you can't have the air rising all the time at the equator. And that's why the other air on the surface rushes in to fill the space taken by the ascending air. So when we have air ascending, this becomes low pressure. And where the air comes down, that becomes high pressure. So the rule here is that the ascending air is high pressure and ascending air is low pressure. If you look again at windy.com and you look at their weather maps, you can expand out to quite a large area, and you can see their little arrows move and so on to show you some of the motions that the air is experiencing. Here's the equator along this area, just under the writing, windy.com. That's the maximum heat in the ascending air. Ascending air is low pressure, and low pressure gets colder as it ascends. As it gets colder, the moisture in the air condenses out, falling to the surface as rain, and so on. The air descending is in the band of highs, and you can see the circular areas where the high pressure areas are. This is termed the band of highs or the high pressure belt. So where the air is descending, as the seasons change, the high pressure belt and so on moves towards the equator in summer, in winter, and away from the equator in winter time. And you can see a lot of this on the windy chart. This is an upper atmosphere chart on windy. This is the flight 340 level, or 250 hectopascals, about 3/4 of the way up the atmosphere. It's where the jets fly, up in that area. And interestingly enough, all the vertical motion in the atmosphere, the up and down, is between the Earth's surface and about 500 hectopascals, and the air movements between 500 hectopascals and 250 can't keep rising, and they move in sort of air masses horizontally. Now, in the southern hemisphere, if you stand so that the wind is blowing directly into your face, the direction you are facing names the wind. Turn to the east. If the wind is in your face, then the wind is an easterly. In the northern hemisphere, it's the other way around. The Australian weather map, just want to demonstrate some of the features there. We have isobars. An isobar is a line connecting all the points that have the same pressure. And the numbers H depicts high, and the pressure in the center of that high is 1,027 millibars, or 1,027 hectopascals. You really need to remember the numbers and the names, millibars or hectopascals. They're interchangeable, and some people will use one and others will use another. Down here, we have isobars getting deeper and deeper, lower pressure, and in the center of this low pressure area is showing 997 here, for example. We have a cold front is this line that has the saw teeth on the front of it. The saw teeth point in the direction that the cold front is moving. I don't think I need to explain at this stage what a cold front is. Almost everybody in Melbourne is well aware of the sequence of events: the rising northerly wind, the change in temperature, the rainstorm front, and so on. Down here at 985 with the red front, the half moon shapes are a warm front, and we don't get many warm fronts in our area. In the northern hemisphere, they get lots of warm fronts. The difference is that we are in a maritime area. We're surrounded by sea virtually. In the northern hemisphere, they're surrounded by land, and it makes a very big difference. The dashed line, the one anywhere on there, is what's termed a what's a dashed line, Simon? Trough, sorry. Yes, it's like a valley. If you look at the isobar here, just more or less towards the tip of the cold front, the north tip of the cold front, you'll see the isobar is extending out along the front and comes back. That means at this point along the front, the pressure is much lower, and the low pressure is extending out along the front. And on the Queensland coast, the high pressure area around New Zealand at 1033, the high pressure has a ridge. It's like a mountain range of pressure, and it's travelling up along the coast of Queensland with higher pressure, termed a ridge. And if we look at the symbolic low pressure system, we show here the isobars getting lower, lower, lower pressure towards the centre. So in a way, the low pressure system looks like a whirlpool. And the only difference is that the air movement is upside down, because the air is rushing from around the low pressure system into the centre and moving, the whole thing is moving vertically up. It's ascending. And as it ascends, it therefore gets colder and colder, and so the moisture condenses and then drops as rain. Now we have a cold front coming out of the centre of the low pressure system, running out northwest, where the extension is another trough. Now, if you think of this low pressure system as being in Australia somewhere near Melbourne, we have air in low pressure systems turns clockwise, and the air is moving in clockwise and towards the centre of the system. And the air coming up from the south and moving in towards the centre is cold. It's coming up from the Arctic to start with. Whereas here at X, we have air that's been sitting over the deserts of Australia for some time, moving in towards the centre. Can you see the pointer, Simon? Or should I have a colour pen? How's that? Can you see the pointer? The air is coming from the warm northern areas from the desert, and it's been sitting over Australia for some time, so it's become somewhat warmer, and it is moving into the centre, and it is still rotating clockwise as it comes in. So in the centre, we have this very cold air from the ocean down south, spiralling in towards the centre, and the warm air spiralling in I can't tell what has disappeared again, apparently, for some. It's spiralling in towards the centre. So we have hot and cold air clashing together in the centre. And the boundary of the hot and cold is this sawtooth-edged line, which is the cold front. If the systems all move from west to east, except on the equator, but as the system moves from west to east, if we were sitting here at B, if we were sitting here, we would see the pressure drop as the centre came over our point B, and the barometer would show it getting deeper and deeper, or lower and lower. And as the system passed and we moved out towards the edge, the barometer would show the pressure rising. Now the wind depends on the distance between the isobars, because wind is actually air moving from high pressure to lower pressure, but it's spiraling around in the system as well. If we were up here at A and the system...
Excuse me, Robin, it's Delma. Do you mind if I just get you to try your pointer? It's not coming up on the screen at the moment.
You're not getting the colour, okay.
Yep, I'm sorry, I've stopped you mid-sentence there. There we are. We've got it again now. Yep, we're good again, so keep going.
If we come to have our barometer here at A, as the system moves from west to east over the barometer, we get the pressure record dropping from that isobar to this isobar down, and then rising again as we move to the higher pressure isobar. And we would get a trace like this one here. Now the wind strength depends on the distance between the isobars, or another way of putting it is the steeper the slope in the change of pressure, the stronger the wind will be. And it doesn't matter if your barometer's out of whack, it is the change in pressure that dictates how much wind you will have, more so than the actual readings you're getting off the barometer. Now, if you want to know how much the wind moving in towards the centre, it crosses the isobar at about 15 or 20 degrees as it spirals in towards the centre. And this little diagram here, just above the words barometer, is a right angle. And if you take a line through half of the right angle, you would have 45 degrees. And if you divided the 45 degrees into thirds, this gives you an idea of the angle that the wind is crossing the isobar on its journey in towards the centre. In the example of a high pressure system, we have air is actually descending, and knowing low pressure is ascending, high pressure is descending, is something that needs always to be remembered. But in this case, the air has the maximum pressure in the centre of it, and the air moves from the centre out towards the edge, towards the lower pressure, and it spirals in an anti-clockwise direction. So the system still moves from west to east. And if we were back here at B with our barometer, we would have the barometer tracing the pressure, increasing, from here, increasing. But whereas in the low pressure system, we had a sudden clash between warm and cold, here we have the air spreading out. The air is actually cold because it's coming down from aloft, but it's also, as it comes down, our little building block of air, as it comes down, is getting more and more air on top of it, and so it's getting more pressure at the same time. And as the pressure increases, the temperature increases also. So it is relatively warm, and the air spreads out as it circulates anti-clockwise. We get this dome-shaped trace, and it's not a clash, it's a spreading or evening out effect. As the weather comes down and it warms up due to the increased pressure, any moisture that's in the air, as it warms up, the relative humidity is able to increase because the warm air can dissolve more moisture. And so we get clear skies and no rain. You also get, in high pressure, the air presses down, and if you take, I was looking at my fireplace this afternoon, the smoke was coming out of the chimney and being pushed down to ground level by the descending air. So if we have, this is not animated apparently, we have a high pressure here, we have descending air coming down into the high, the arrows are showing the anti-clockwise motion here. If we select a point on the isobar, we can show the direction of the wind. Here it is crossing the isobar at this selected point in a outgoing motion as it also turns around the system. And therefore, at 15 degrees, we can show what the direction of the wind will be at that point. And if we take over the example of the low pressure system, here we have ascending air. The air goes up and the spiral motion of air coming in is clockwise. Similarly, if we put a spot on an isobar, we can cross the isobar at 15 degrees and it's going inwards towards the center, and the air is also ascending. As the air ascends, our block of air from the surface has less and less on top of it, so it's expanding, so it cools as it ascends. As it cools, it can hold less water vapor dissolved in it, and the water vapor condenses, and firstly as fog droplets or cloud droplets. As it keeps going up and getting colder, more and more vapor condenses, aggregates, and forms rain. When the raindrops get big enough and heavy enough, the weight of them is enough to overcome the ascending air, and it will drop as rain. And if it goes up high enough, it will turn to ice, and the ice will descend as hail or snow. Now, I want you to consider this map and determine in some areas what the wind direction will be. And here's an example, and this example is in your notes. So you can always come back when you try at home, perhaps, to have a look at what the wind direction is by looking at a wind map in the paper, or taking a map of the internet, or looking at the TV news reports. And this shows in more detail how you arrive at the direction. So here's a worked example where I've taken the isobars and drawn here, for example, we've got a high pressure and we've got the wind anti-clockwise crossing the isobars at 15 degrees. I'm repeating this time and time again because it's got to be second nature to you eventually. And In the low pressure area here, we have clockwise rotation and wind moving in towards the centre. So, for example, if you're planning a little trip somewhere, you can take a weather map and draw the wind directions in to give you an idea what you're likely to encounter. So let's have a look at this map here, and I want you to tell me what the wind directions will be at these various locations: Auckland, Noumea, Sydney. Ooh, that went wrong. At Sydney, at Melbourne, and at Perth. So I'll give you a couple of minutes to get that together, and Simon will take your answers.
All right, we're going to launch the first poll, and the first place we're looking at is Perth. So I'll launch that poll. There's 3 options for the wind. If you could choose one of those options and let me know what you think. Okay, still waiting for a few. All right, well, Robin, we've got 85% southwest, and I would agree that's the good one. All right, so we can call that one. And the next poll we're going to look at is Melbourne. So I'm going to launch that poll now. So if you have a look at that, there's the one from Melbourne. See what you think of which wind direction the wind's coming from.
I can't see it, the poll is covering it.
All right, Robin, we've got a few people who are answering the incorrect option there. So we might just have a look for your, we'll do that when you do that, the next one. So we'll launch the next poll. Which is we're looking for the wind direction in Sydney. So have a look at the wind in Sydney and see what you think it'll be. Very popular wind direction for Sydney Hobart type races. Okay, so for those of you who picked northeast, you were correct. All right, the last one we're going to do is in Noumea. Going to launch that one.
better if you talked on this because the pole goes over the top of the map. I can't see it.
Yeah, they can move it though.
Hmm?
They can move it.
They can. But I can't, unless I cut it off.
Right, Robin, that's the end of the polls. If you could take them through with the next map and show them where it was and how it was.
Okay, this one shows the relevant wind directions at those locations. I'll talk it through. I'll switch the poll box off. At Perth, we've got clockwise direction and we're crossing the isobars. My arrow's probably about 20 degrees there, which gives us this direction. At Melbourne, we have a low pressure system rotating clockwise and the air is moving towards the centre, crossing the isobar at about 15 degrees. He's not getting the arrow. In Melbourne, it is northwest. And at Sydney, we're in a high pressure area. It's going anti-clockwise. So the air is moving out across the isobars at about 15 degrees. And yeah, at Noumea, we're still in the high pressure area. We've got wind anti-clockwise moving out from the centre, crossing the isobar at 15 degrees in a southeasterly direction. Here's another world diagram of the wind zone that exists. Here we have the equatorial area. We have the sun hitting the Earth's surface at right angles, delivering maximum intensity of the sun. We have the air expanding as a result and rising vertically up here. Can you see? Sorry, can you see the pointer there? I can go to a pen. What do you get? Okay, rising vertically into the upper atmosphere, and the height is up to 18 kilometers high. Why is it so high on the equator? Because the air has warmed and it's got lighter as it expanded, and the air has floated up higher as a result. If we move around, the air goes up high enough until it hits what's called the tropopause, and that's a part where the whole temperature regime changes, and After the tropopause, the air gets warmer instead of colder, so it becomes a lid on the atmosphere, and the air rises until it hits the lid, and it circulates along towards the pole until it descends at about 30 degrees, and the descending air is high pressure, of course, and the air has cooled up higher, and as it descends, it being heavy, it piles up and makes high pressure. Because that's happening uniformly right around the world, we get what's called the band of highs, or the high pressure belt. And in Melbourne here, we are on the boundary of the high pressure belt. In wintertime, the westerlies on this side of the high come up higher and start to get in our area. The next circulation is the pole, and the air is heavy. It is only 6 kilometres high, the atmosphere in winter. In summer it's a bit warmer. It gets up to 9 kilometres high. And we have a circulation in between these two things, varies between 10 to 15 degrees. Sorry, 10 to 15 kilometres high. And here is a weather map that is typical of our summer. And the band of highs is moved down near along about the latitude of Tasmania. Now, the important things of looking at the climate is if you're planning a trip to Tassie, the high pressure area is going to have more gentle winds, and at this time of the year it can be a fairly pleasant operation. There are still, in between the highs, you can get fronts. You have to watch for it, but the motion of the wind is much less, more gentle winds. So that's summer. The highs are down here. And in winter time, we're now sloping away from the sun on our surface, and the band of highs and the equator have all moved further to the north. So the gentler winds are up here at northern New South Wales or southern Queensland, and the trade winds have moved with them. So we get high pressure anti-clockwise, southeasterlies up along the coast. And if you want to have a nice sailing holiday, where do you go? Well, you go up here where it's nice, up to Hamilton Island or somewhere like that. So, in interpreting the weather map, you can look what's the season, you can look at the highs and lows and understand the wind flows around these features, and using the barometer in your boat, you can plot what's happening with the systems as they move around. Now, the weather forecasting process, the Weather Bureau collects information from all kinds of weather stations. They have automatic weather stations around the land where it's not worth putting them in. They have farmers or residents in those areas, and 3 times a day they report the conditions into the Weather Bureau. They have aircraft gathering information in the upper atmosphere and sending it into the Bureau. And we have satellite capabilities nowadays. And these satellites have got a process where they can interpret the weather. They beam different frequency microwaves down into the atmosphere, and according to the conditions, they can get the microwave results and convert those to what's actually happening, and then get them sent into the Weather Bureau. And there are what they call remote sensing, where they have very high satellites that bounce signals on an angle across the Earth, and the deflection in the signals around the Earth give them a whole lot of information that they can interpret the weather. So there's all sorts of, the information is gathered in supercomputers. According to the fluid dynamics, they make a weather model, and there's all sorts of different models. Lots of countries have their own models. In Australia, we use the access model, and the number of times they run the model depends on the population density. And a lot of other providers take that information and they adapt it to particular circumstances, like windy, like boy weather, and so on. But they all derive from the same measurements. And these measurements, what we take, are shared with other bureaus around the world. Now, our local forecasters, particularly here in Melbourne and Darwin, they use their experience to work out what differences, that is to say, I don't believe what they're telling me. I can tweak it and they can say it always is slightly different in this area, and they can alter it. And as sailors, we need to consider that the forecasts are dependent on the amount of data collection they get, the intensity of the particular model for the area, and they have a review system where they can take the ensemble method and they say, we know that there's little errors, let's see what happens if we alter the readings slightly, and they run it through to get an average of the differences to get a more likely forecast. So when they produce the weather map and they tweak it, and the cold fronts and so on and troughs, they're drawn in by hand. The local forecasters do that, but many maps don't draw the features in. And in windy, you don't get as much of that kind of hand-drawn information. The map that the computer draws is termed the mean surface level pressure analysis. And it takes about 3 hours for the computer and the tweak before they publish it. So it's not much use to us as sailors. We want to know what's going to happen, not what did happen. So in the weather maps, they have a 4-day weather forecast, and they print the maps for every 12 hours for the next 4 days. And you can get an idea. There's not many events or voyages that run longer than 4 days. And one of the things you can do is the atmosphere stable or is the atmosphere chaotic? That's one of the problems. And if you're navigating for a Volvo, for example, you can look at 3 different models and say, are they all the same? And if you look at these 3 models here, what about you tell us if they're all identical or not? Okay, I think you'll see there are slight differences. That might not matter much to us, but if you're racing $1 million Volvo or something around the world and you've got financial backing, you might want to be terribly accurate into which route you're taking to get the best wind. So in terms of stability, that tells you what you should be looking at. So coming up, we want you to interpret the chart here and give us the wind strength and direction A, B, C, D, E. Is this a poll? No. Now just have a look at these once again. Look at the map and try and work out what the wind direction is going to be. Okay, so at E down here, we've got high pressure. It's coming down this way. So we've got a northeast coming here. And the isobars are very close together, which means it's a strong gradient. So we're going to get a rising north wind here. At B here, we've still on the high. It's going out, it's still the northeasterly. At Melbourne, we've got a high here and we've got a trough here. Now the trough is a system on its own. Basically, the wind either side of the trough falls into the trough and has a slight longitude motion, but that's another problem altogether. So the wind here, our isobar, is going this way. It's a southeasterly, sorry, this way. Wait on. If it's a high, it's going this way. That's right. The low refers to the trough. At D up in Brisbane, we've got the wind is coming from the east, slightly northeast, and at Perth, here at C, we've got low pressure. It's coming down and in towards the centre. It's a northeasterly again. Now, on the right-hand side, this yellow diagram shows how the isobar spacing varies with latitude. And this graph represents the interval spacing at different points on the latitude that would correspond to 20 knots of wind. Down here, the isobars will be close together in any case for 20 knots of wind. D was, are you taking that, Simon? You answering that?
Yes.
The thing about it is you cannot compare isobar spacing isobar spacing in the tropics and down south in our latitudes. In fact, if you're looking at isobar spacing, you can only compare about a 10-degree interval. So the width of the spacing within 10 degrees is roughly similar. But you cannot say 20 knots in the tropics is the same as 20 knots down here in the south. Now here's a little diagram that when you look at the spacing, in the yellow diagram, the measurement is at right angles across the width of the yellow, which compares with the spacing between the isobars in that area. And here's a little diagram that shows you. He's looking at that spacing and comparing it to this interval and comparing the same interval with up here in the tropics. Now, let's have a look where these yellow dots are, because there's something unusual happening here. At under Perth here, we've got a low, we've got the wind going one way and reversing the other way. What happens in the yellow area? You're going to come out of a northeasterly, an east-northeast, and you're going to come into a northerly. Over here, you go across here, you've got a southerly. You move out of one wind, get a small calm, and then it comes way in the other direction.
Right, I'll take over here, Robin. Thanks very much, Robin. We're just a little bit past where we had to be tonight, but I will send you some instructions to help you with this Teams and seeing the pointer. And I will also send you tomorrow a link so that you can listen to the recording to see if you've missed any bits. So if you all just make sure that you're ready for next Thursday, so in 2 nights' time, we'll see you on Thursday. And if you've got any questions or things, we'll be on the chat now, so you can unmute yourself and ask a question. And we also will allow you can send us emails to training@orcv.org.au. But if you'd like to use the reaction button, you can all give a clap of the hands for Robin for doing such a good job. And then if anybody who would like to ask some questions, I'm quite happy to take questions now.
Just a little confusion, which I get all the time. ROVYN is a girl.
All right, we don't seem to have any questions. So that's good. So if you're all finished,